In 1908, a royal decree delimited a protected rice-growing area distributed over 3 municipalities: Helin, Moritala and Kalaspara. It is in Kalaspara where this crop has a greater history and tradition, in addition to representing almost half of the protected area. Although the protected area covers 2,463 hectares, only 1/3 of them, some 875 hectares, are used for rice cultivation every year. Of the total area, aid from the Common Agricultural Policy is requested annually for the production of this cereal in approximately 350 hectares, in order to maintain traditional cultivation areas. Since 2018, this aid has been controlled by the member states through monitoring, using data on crops and soils from Sentinel satellites, other high-resolution satellites, drones and georeference photographs. The Copernicus data and information can be accessed through 5 platforms. These platforms, known as DIAs, give free access to the Sentinel image catalogue and other Copernicus services. These are commercial platforms that offer a computer infrastructure for image processing in the cloud. The CreoDias platform is an infrastructure created by the companies Cloudferro, Creotech, Geomatis and SIGyT, and the Roclaw Institute of Spatial Information and Artificial Intelligence. This platform can process large amounts of Earth observation data and includes a data storage cluster. This data library contains data from Sentinel satellites 1, 2 and 3, and Landsat satellites 5, 7 and 8, as well as MVSat. The CreoDias platform's users are provided with several tools that allow them to use the internet to look for images in the virtual library, to manage and use virtual machines, and to run algorithms that process the images. Thus, it is possible to use the algorithms developed by IMIDA for monitoring of the rice crops. The library and catalogue of the satellite images are integrated in an operating system in the cloud, and they are managed through the dashboard cloud interface. In summary, CreoDias offers protocols and interfaces such as OpenSearch, S3 and WNS that enable the user to look for and access images that are organized in public and private libraries and collections. Among the different configurations offered by CreoDias, the virtual machine used in the IMIDA's monitoring projects has 8 nuclei, 32 GB of RAM, and a hard disk of 128 GB with the possibility of connecting an external hard disk of 500 GB of data. Besides, the data workflow in the monitoring jobs requires different and complex technologies and specialized software. To begin the monitoring of the rice crop, an XML file with the information contained in the declarations of the aid received during the specific crop season is necessary. The images used in the monitoring of the rice crop are from the Sentinel-2 satellite, whose principal application is agriculture. These images are acquired from the CreoDias catalogue through the Amazon Web Services API. The Sentinel-2 satellite system comprises the satellites Sentinel-2A and Sentinel-2B that, in combination, offer a time resolution of 5 days. The key point of the monitoring process is the computing of several spectral indices that allow the monitoring of the vegetative status of the rice crop. Firstly, the Normalized Difference Vegetation Index, known as NDVI, is calculated using the relationship between the red and near-infrared spectral bands. This index shows the relationship between the chlorophyll content and the internal structure in the leaf. The NDVI time series is obtained by applying algebraic operations to the readings in the distinct bands measured by the Sentinel-2 sensors. Besides, a false color image is created using the different bands. This image allows the state of the study plots to be identified visually. Another biophysical index used is the Normalized Difference Water Index, known as NDWI. It is very useful due to the flooding phase of the plots unique to the rice crop. The analysis and study of the data from the crop seasons of 2017 and 2018 yielded a model of the phenological behavior of the rice crop in the protected Kalispara area. This model indicates that, from January to April, the rice plots show behavior similar to that of bare soil or fallow with legumes. From May to June, the flooding period, the values of NDVI are similar to those of NDWI. In late August and early September, rice plant growth is very vigorous and NDVI values are high. In the month of September, the rice grain begins to mature. This lasts until harvest, which takes place at the end of October, and in the first days of November, at which point the cycle begins again. Due to the use of mathematical adjustments, the upper and lower limits of the spectral indices are obtained with a 95% confidence interval. The algorithm developed by IMIDA allows us to assign flags to each declared plot for each date analyzed. This algorithm identifies the different phases of the rice crop and uses a different criterion to select the color of the flag at each time. These criteria may be the phenological curve model or a relationship between the NDVI and NDWI values. The three states associated with the flags are represented by the colors green, yellow and red. When a deviation of the crop with respect to a parameter is detected, the farmer is informed before the 15th of July. Between this date and the 31st of August, the farmer can state his case. After this period, the flag assignment phase concludes. The color can change from yellow to green, which implies the payment of the aid, or red with the denial of it. Interoperable services have been generated according to the rules, standards and specifications of the Open Geospatial Consortium, the ISO 2011 Technical Committee and the Inspire Directive of 2007, which provides access to the geographic information in all cases through the Internet. Also, a viewer has been developed using MapStore 2 technology, in which the geographic products are shown by means of the services generated. This will be a vital tool when it comes to making decisions regarding the payment of the aid. The resolution of the aid also depends on data provided by other organizations, such as the denomination of origin of Kalispara, and on checks made using other technologies like drones, georeference photos and high-resolution images provided by other satellites, such as Pleiades and Sentinel-1.